Um, okay, right now we want to share a little bit about clustering. It's an unsupervised learning problem. Key objective is to identify the distinct group called cluster within some notation or similarities within a given data. The idea behind K-means clustering is that a good clustering is one with which within cluster variation is as small as possible. So objective of clustering, you subdivide the given sets of training data, x is equivalent to x1 to xn into a number of k subgroup with unknown class label of the training vectors. Useful information may be extracted from x1 to facilitate pattern recognition and statistical analysis. So the topics as follow: similar metrics and clustering strategy, k-means algorithm and its convergence property, expectation maximization and clustering algorithm, self-organized map SOM, and by clustering method. So similarly, metrics and clustering strategy, let X denotes the complete set of training data. X is equivalent to the X comma to the xn, and then where X encompasses Rm. So it becomes a matrix. As you see, the clustering delivery has to be divided into n training into k group. The partition group specified that this vector should be placed into the same group, feature extracted, similar metrics, learning model, and clusters identified. So similar metrics, uh, Euclidean space, centroid, and non-Euclidean space is a mediot. Euclidean space distance is L2, norm ED. ED is square root of summation of observed value minus xi minus yi square. Um, and Euclidean space also have a Manhattan space MD. MD is a summation of absolute xi minus x yi, and maximum distance MD. Max D is equals to maximum absolute xi minus yi. So Euclidean space is a meteoroid cosine distance using dot product. So cosine distance equals to 1 minus cosine theta. Uh, J cut distance equals to 1 minus x union y divided by x intersect y minus by x union y. So there is a Jacob distance. So the similar metrics are Euclidean space and non-Euclidean space. Euclidean space is Euclidean distance, Manhattan distance, maximum distance. Non-Euclidean space is a cosine distance and Jacob's distance. So consideration for clustering discovery, the number of cluster k divided by n training vectors in k disjoint cluster x is equals to x1 union x2 to xk. The value of k is pre-assigned to determine empirically node vectors. Each cluster is assigned a node vector denoted by wk, k1 to k. The task of clustering is to find an optimal set of k node vector. Topography of node vectors. The basic objective function of clustering is just the function of x. Node vector may be organized on a topographical order grid. Example SOM. Objective function of the unsupervised optimizer is set the foundation of the learning rules which one both intra-cluster and inter-cluster metrics. Minimum intra-cluster compactness of maximum inter-cluster separation. Topologically adjust inter-cluster criteria. Example SOM. Iterative learning procedure, the membership of the disjoint cluster, where x is x1 union x2 to xk, and then node vector wk, k equals to 1 to k. Evaluation criteria for selection among the multiple trials. So this is a discovery method. K means clustering algorithms. The assumption of the numbers of clustering is fixed. The K means algorithm subdivide n training vectors x equivalent to x1 common to x1 to xn into k disjoint cluster. So x1 is x is equals to x1 union x2 to xk. So let k cluster be respectively labeled by C, which is C1, C1 to CK. Maximum likelihood of clustering criteria, assuming X is generated from a set of K locally distributed probabilistic model parametrics by theta equals to theta 1 to theta k. So it's a parametric equation. So k-means objective is to find the model theta uh, star which has statistically highest order of likelihood to generate the observed value, i.e. The augmented maximum log p um, given x, um, which is met theta probability model, yeah, given the condition of theta. So K means objective is to find a model that has the statistical highest log likelihood to generate the observed value. K means clustering criteria is under the assumption of independent distribution where probability x given a condition of theta is the sum, the full sum of t equals to 1 to n p x t partial of your theta. So now it's focused on the specific vector xt to maximize the likelihood. Note that xt is the most likely to be generated by the model ck, where k is argued maximum p xt uh, theta for all j where it's equals to 1 to k. So the ultimate individual likelihood is p xt theta is equals to p xt theta k. So under the assumption, the overall optimal likelihood is p probability of x in a given condition of theta is equals to summation of all cluster and k equals to 1 to k, and summation of xt encompassing ck probability of xt uh, given that theta k. So this is k-means clustering criteria. So given that the k-mean clustering criteria, assuming that each cluster is governed by the Gaussian distribution with isotropic covariance, p is equals to xt, theta is equals to 1 over square root of 2 pi sigma power m, and even the expression minus um, absolute of xt minus mu to a power of square divided by 2 sigma square. So where uh, mu k and sigma denote the respective centroids and standard deviation of k cluster node, taking both log on both sides of the equation 1 minus log x given theta uh, is proportional to the summation or the total of k1 to k and summation of k encompassing c k or log in a given expression xt given theta k, right, where summation k1 equal to k given the summation of t ck, where you have log axy equal to log ax plus log ay, log axy equals to y log ax. So this is basically the logarithmic function. So maximize that likelihood among the maximized criteria in terms of the sum of square distance SSD. The objective function of k-means is to find the centroid to best minimize the SSD cost function, where estimate of SSD is equal to summation from k equals to 1 to k and summation of xt encompassing ck absolute as xt minus mu k squared. So the clustering parametrics equation by clustering the centroid theta is equal to theta 1, theta 2 to theta k. So this is the k-means of clustering criteria. Iterative, the max optimization of k-mean algorithm. Our initial step is to choose either k initial centroids, mu k for k equals to 1 to k are randomly assigned. Each training vector xt is randomly assigned to arbitrary cluster, say ck. Winning identification step fix the membership parameters and focus on the updating xk to best minimize the SDD cost. Um, so the winning cluster of the nearest central is known as the winner, and k argument minimum x t minus mu k x is encompass ck centroid update steps when a new vector tx is added in the clusters ck, the old centroid of that cluster, i.e. is mu ko will be updated as follows. So mu ko tends towards mu k is 1 over n summation of xt encompassing a ck xt, which nk denotes the total number of vectors in a ck. Okay, so uh, monotonic conversion of k-means, the theorem that k-means iterative procedure monotonically converts to a local optimum in terms of SSD criteria. Winner identification steps you let CKO and CK denotes the O and new cluster. The distance to the new cluster has to be shorter than the O, hence reducing the cost function. So summation of K1 to K and summation of XT encompass CK of XT minus mu O um, sum of square less than the summation of K to K1. The only difference is you can see the CK of new and the O, so that it has to be the identification step to the K means, where mu KO denotes the centroids before the centroids update. So centroid update steps, the gradient of the objective function OF are taken with the respects to UK, where they twice continuously differentiate. The gradient of OF vanish at the local minimizer, and the first order gradient of OF with respect to UK and equating to 0. So it looks like it's a parametric equation. Then you actually differentiate that, so then you get a minus 2 summation of xt. So it looks like this is a conversion means, meaning to differentiate to a conversion by differentiation. So the monotonic conversion of k means, which leads to mu k is equals to 1 over nk summation xt encompass ck to xt. So subsequently, the summation of k equals to 1 to k and summation of xt equals to ck covers from xt to mu o must be less than or equals to uh, everything is the same except the cko summation of the cko. So the cost function monotonically decrease in every iteration. The iteration algorithm of k-means progressively improve the clustering accuracy. Since the cost function ex cannot be negative, the iterative process will terminate at some points. So k-means often converge to a local minimum. The performance of each k-means depends on the initial condition. So in the sklearn k-means, there are some class over there. So class sklearn cluster k-means, and you have n cluster equals to 8 initial class k-mean plus plus, then attribute cluster center, nd arrays of shapes, uh, coordinates of the cluster center. If the algorithm stop before fully converging, it will not consistent with label nd array of shapes, label of each point. Initial is equals to float, so sum of square distance of samples to the closest cluster center, number of iteration runs, and IER, number of iteration run. So optimal number of clustering uses elbow method. One of the main challenges is unsupervised learning is to find the optimal number of cluster within cluster SSE. Sum of a square between each observed vectors, it is dominating on the centroid. So within the clusters, the sum square error and intrinsic metric qualify the quality of the clustering. The attribute initial after fitting the k-means model computes within cluster SSE. A graphical tool is now called elbow method identified the values of k when the distortion begins to increase. Distortion is the definition of sum of square distance between each observed vector and its dominating centroid. So each steps of a k-means algorithm refers to the choice of centroid to reduce distortion. So the higher distortion, the number of clusters has a lower distortion. Um, so expectation and maximization EM model. Expectation maximization model is a extension of k-means algorithm by Dempster et al. In EM, expectation maximization of the model parameters, theta is equals to from theta 1 to theta k, are trained to best fit the data under a statistical model. Which you look at a cluster like container, it has a mu1, and then the one in mu2 has actually a different clustering. So the proportion membership from HT uh, to K is a proportion of the probability of X1 given the condition of a theta K. So with that, K means users hard membership assigned to a training vector must be assigned to one or only cluster. EM users soft membership assignment, the membership of KXT may be proportional assigned to the cluster. So expectation maximization algorithm in many real-life problems of machine learning, there are many relevant features available to build a machine learning model, but only a small proportion of them are observable. Since the value of the not observed latent variables are not available, the EM algorithm tries to use the existing data to determine the optimal value for those variables and then find the model parameters. And the latent variable model consists of observable variables along the unobservable variables. Unobserved variables are those variables in the data set that can be measured, whereas unobserved, latent or hidden variables are inferred from the observed variables. So expectation maximization algorithm EM um, is the observed value that is variables that can be measured and unvariables, unobserved, which is latent and hidden. So observable and unobservable variables. So EM, which is expectation maximization algorithm, given the set of incomplete data, start with the set of initial parameters. Expectation step is E step. By using the observed available data of the data set, try to estimate or guess the value of the missing data. And finally, after this step, we get a complete data having no missing value. So maximization step is the M step with a complete data which is prepared in expectation step update the parameters. So in short, expectation steps, you update the variable. M step, you update the hypothesis. Yeah, so it's the expectation and maximization algorithm. So you update the variables and update the hypothesis, and update variables, update the hypothesis. So application of EM expectation and maximization algorithm is the latent variable model has served real-life application in machine learning. In filling data during a sample, it applies a different domain like uh, NLP, natural language processing, and computer vision. Using the image reconstruct in medical and structural engineering, use the estimate parameters or hidden Markov, HMM, hidden Markov, and mixed model like Gaussian mixture model GMM, using finding the values of latent variables. So EM clustering, EMs try to find the optimum parameter ops which maximize the log likelihood uh, equals to arguably maximization of a GP uh, given X, given the condition of theta. So that is basically probability of x given theta, total sum of k1 to k to x encompassing k probability of x given theta k. So you assume all equal probability, um, and that's under such assumption the independent distribution follows. So there is independent distribution for EM clustering, which is expectation and maximization. So as mentioned, expectation, which is the E steps to update the variables, and M, which is maximization, is to update the hypothesis. So EM clustering criteria, you log P of X given the condition of theta, then you summation of T and summation of K, probability of theta K given X, and the log P given X, given theta divided by K minus the log P theta given T. So noting the summation of K and log 1 over K equals to minus log. So at the end of the day, log Px given theta um, has this particular expression. So the likelihood log becomes log Px given theta equals a summation of T and summation of K, HTK log Pxt given theta K minus HTK log HTK minus the uh, n times log K. So EM criteria for basic GMM model, Gaussian mixture model. The EM criteria is applicable to many statistics distribution model, including the Gaussian mixture model. Each of the mixed cluster in a Gaussian has a Gaussian density distributed parametric by both of the centroid mu and the covariance. So probability xt given the condition of theta equals to a normal of a mu and summation of k where k equals to 1 to k. So assuming isotropic Gaussian distribution, the conditional probability density function will become p xt given the conditional theta equals to 1 over square root of 2n sigma exponential minus absolute observed value minus mu or square divided by 2 sigma square uh, encompassing K in the given equation. So EM criteria for basic GMM model, assuming that all clusters have an isotropic distribution, summation theta I, substituting the equation C, the equation B optimize the categories as given by minus log P x theta is equals to minus 1 over 2 sigma square, then you sum, and then that's where the criteria of a basic Gaussian uh, Gaussian model. Yeah. So GMM will be Gaussian mixture model. SDS and entropy criteria. The criteria objective is the sum of square distance SSD, sum of square distance, and entropy criteria defined as a given equation. EM, which is the estimation maximization optimizer, aim to maximize EM uh, with respect to mu, where k equals to 1 to k. It's faster to apply iterative method to find the optimal solution which minimize SSD entropy criteria. So expectation maximization algorithm aims to use available observed data of the data set to estimate the missing data, and then latent variable, then use the data to update the variables of the parameters of the maximization step. So expectation is using a guess, maximization is using the hypothesis, and then go back to expectation. So initial step is to initialize the parametric equation with a set of initial value, then give the sets of incomplete observed data to the system and assume that the observed value then comes from a specific model probability distribution. So expectation set use the observed data to estimate or guess the value of missing or incomplete data is used to update the variable. So maximization step use the complete of data generated by expectation is to update the values of the parameters, update the hypothesis, checking the conversion steps, check whether the steps are convergent or not. If yes, then stop. Otherwise, repeat those step 2 into expectation and maximization step until conversion occurs. So basically, it's still conversion. So iterative of EM expectation maximization for basic Gaussian mix model. So initial step, you have a E step, which is estimation the node vector of the centroid suffix, the membership proportion of xt allowed to the n cluster can be updated. And then the M step basically is the maximization of the membership proportion. Uh, goes to ht, k, and k equals to 1 to maximum k are fixed. Then the node vectors can be updated and weighted centroids of all n training vectors. So this example closely to the Android updated in the k-means, then you check for conversion. You initialize, you do the E step first, which is the estimation, and then you see whether it converts. If don't, then you go to the maximization, and you have estimation, and then if it converts, then you stop. So basically, this is the whole idea of iteration of an EM algorithm. The EM algorithm for data argument uh, augmentation using the numerical methods, which finds the pastoral mode that the values at each probability n given x or log p n given x is a maximum. It does not provide full information for the pastoral distribution. So consider the genetic link within Rao 1973, in which there are observations where x equals to x1 to x4 with cell probability, so like um, half plus half over uh, n comma 1 over 4 1 minus n and all. So the likelihood is then um given as below, right? So if we take the standard reference prior to BE 00, then the pastoral is a beta distribution BE. So the EM estimation maximization algorithm for data augmentation, the data X is augmented by further data Z to produce the augmented data Y, and should note that the distinction between the parametrics of a model and the augmentation of the data is artificial. This augmentation consists of simply splitting the first cell into two cells with probability half and then n divided by 4 uh, what quarter, and the advantage of this likelihood takes much simpler form. So the form is actually a little bit simpler. If we take the standard reference prior to the BE, which is the beta distribution, then the pastoral is the beta distribution. Right, the greater simplicity of the model involves splitting x1 into y0 and y1. So the E step is the estimations step on the EM algorithm is to find the pastoral mode is an iterative method starting from some guess where n is 0 for the value of n. At the stage t, the current guess is n. In each state, it has two steps. In the first step is E step, computes q equals to nn equals to e log p ny. Expectation or log likelihood being computed at n equals nt, so that q equals to nnt. Then you have integration over a log. So m step is the second step. Maximization step is the aim to find the value of nt plus 1 of n which maximize q. This particular example of y equals to q1 for I equals greater than 1, q and nt is equals to e y plus y1 plus y4 minus 1 log n plus y2 plus y3 minus n. So the n step maximization step, you differentiate that, then you get equation equal to this 0, so we can deduct that n t plus 1 is equals to a certain equation. So the MSEP, since y1 has a binomial distribution with pi or pi equals to quarter nt divided by 1 plus 1 quarter nt, so where nt equals to quarter nt, then you come out with iteration process. So that's the M step. Example, if the value observed as x1 equals to 125, x2 is 18, x3 equals 20, x4 equals 30. So starting with a guess number 0.5, and t plus 1 is equals to nt follow the equation, and then you put in x1, x2, x3, x4, which is what is given here. Yeah, x2, x1 to x2, x3, x4, and then you find what at the same time you have a quadratic equation. So from the implicit formula, you try to get a quadratic equation which will give you two values, right? And then where b squared goes to uh, minus b plus minus square root b squared minus 4ac divided by 2a, then you actually find the values of the quadratic formula. So depth of data, the decisional methods of acquiring data is difficult, expensive, impractical. Sometimes only available option is to use data augmented tactics to extend the data set. So like most images, tools, audio, videos, and social media such as YouTube are not clearly labeled as copyrights. So in short, sometimes you don't have enough data. So the augmentation, data augmentation, especially this example is to overcome this problem. So self-organizing map SOM model and K-means aims to find the cluster so that the inter-cluster data distribution are as compact as possible. SOM, which is self-organizing map, impose an additional condition on the neighborhood sensitivity, which requires topological adjacent nodes to exhibit some proximity when mapped to the original vector space. The input space is represented by the lower level with the training data set x1 where t equals to 1, 2 to n, where xt equals t equals to 1, 2 to the n. The output space is represented by the upper layer, which is arranged as a k distribution grid mesh comprising of L1, L2 to Lk nodes. Each nodes represent a cluster denoting Ci, where I encompass I L1 times L2 to Lk and parametrics by the node vectors when mu I. Yeah, the objective of SOM learning is to train collective the nodes of weight vectors, mu I of all nodes in the mesh so that the mesh can be best represented the original training data set. SOM, which is the self-organizing map, initialize states is you random initialize is objected. SOM involve two steps of learning algorithm. The inner loop, the centroid of the cluster are updated and multiple epochs are to be executed in the inner loop before it exit to the outer loop. So each training pattern ST for all t equals 1, 2 to n will sequentially process with the following updating process. So identification of the winner cluster whose central is closer to XT will be identified as the winner. So I is equals to I encompass of I from L1 times L2 to Lk in the argument where minimum of xt to minus mu I. Update the winner node, the node central of the I node. The winner is modified by the following mouth. So a change of a mu I is equals to n times xt minus mu I, where n is a small positive learning rate. So the SOM iterative learning algorithm, the central update of the neighboring co-winner is modified additively by the amount. So a change of a UK equals to n hack ki minus bracket xt minus mu I for all k encompassing I, where it encompass of ki as a pre-specific neighbor sensitive function. Continue the next training data set until the entire purge has been completed. Once the inner loop is completed, the outer loop update, and then the gradual shrinking by learning the windows is effective of the neighborhood is gradually shrunk, reducing the window size as follow. Um, yeah, so decreasing the parameter size as follows. So Cohonian law. Covalent law or adaptive law is given by Wij T plus 1, and you break this into Wij T plus N encompassing of T, where Xj equals to T minus Witj, where Nt is adaptive vectors, learning rate, and Hack T is the symmetric function centering around vector U, allowing greater adaptation and neural close from mu, and a weaker adaptation of a neuron far from mu. The initial neighborhood sensitivity function equals to 1, where Xj is the input vectors. So example of a coherent self-organizing map FOM, given two nodes of a coherent level with four inputs represented by a vectors. The initial weight matrix is W11, W12. Yeah, so you have that. The network is cluster input vectors with four components into two categories. The learning rate is alpha not equals to 0.6. The neighbor is when ns equals to 0. Update the winning nodes. So the first input vector is x equals to 1100. The input intensity dj of node 1 and 2. So you have a d1, 1 minus 0.2 plus 1 minus 0.6 plus a square plus 0 minus 0.5, where you have your x 1100, right, first input vector. Then you have your d1 equals to 1.36. Yeah, then your d2, which is 1100, then you have your d2 equals to 0.99. So for coherent self SOM self-organizing map, the input vector is close to the output node. This is the winning node, and the weight of the winning nodes are updated. W21, 22, 23, 24 with a new times the alpha minus your x will W. So you have like or it's given at 0.4, 0.8.4.7.3, 0.8.4.7.3 plus 0.6, right? Uh, then you have the matrix, and then you minus off, so you will give you a new node. Then the new weighted average will be as given, right? Yeah. So the birth step repeat for input factor 001, 1001, and 011. So you do all these three. So a coherent self-organized map, the learning rate is decreased by some sequence of patterns are entered into the network for further training. After many iterations, the weight metrics appear to be convergent, right? And then the network is able to cluster the four input into two groups, 001 with 0011, first node winner, so there's a winner. The output is from first group equals to 1, 1100 with 100, the second node output from the second node is 1. So the first column of the weight matrix is the average of the two vector placed in cluster 1. Um, the second column is the average of the two vector placed in cluster 2. So application of SOM it's a group technology like manufacturing or manufacturing cell. So that has a gas, and then you move on to the next one. So application could be a group technology concept, significant reduce the setup time, plays an important role of success or implementation of flexible manufacturing process, increase productivity and multi-modes to small to medium batch size, self-organized map. Neutral network can be used for identification of family parts, requires similar manufacturing process. The arrangement of these machines minimize the number of parts visit more than one cell. So traditional method of solving problem, the use of clustering method, which consists of groups and machine into a machine cell using a machine part matrix. So this is the reference. Yeah. Oh.